The machine is driven by an AC vector motor driving through a Scotch yoke mechanism which generates sinusoidal motion on a reciprocating head. The reciprocating head is loaded against the plate specimen by means of a load yoke. The load yoke is attached by a beam to a servo motor and spring mechanism. A force transducer directly under the load yoke measures the applied load. The fixed specimen is mounted in a fluid bath, itself mounted on a heater block. The heater block is mounted on flexures and restrained from motion in the horizontal plane by a piezo transducer. This measures the friction force. The specimen bath may be indexed perpendicular to the reciprocating motion for alignment purposes and to allow different specimen wear tracks to be worn on a single sample. The specimen plate is fitted to the bottom of the bath using two countersunk screws. It is important to adjust the thermocouple position to make sure it touches the edge of the specimen if possible. If the bath has been removed for cleaning, make sure that the thermocouple is reconnected. Standard specimens include a 6mm ball, a 10mm ball, a 6mm diameter cylinder specimen, and a 12mm diameter area contact specimen. The 6 and 10mm ball specimens are carried in brass tubes, which aids handling and identification of wear scar location. The ball specimen carrier is attached to the reciprocating head using a clamp plate with a hemispherical seat. It is important that when the machine is running, the cam housing is level. The specimen position in the reciprocating head may need to be adjusted to ensure that this is the case. The 6mm ball specimen is in a smaller diameter tube. To fit this to the reciprocating head, we use an intermediate sleeve. To fit the line specimen carrier, we need to loosen the clamps sufficiently to allow the line contact specimen carrier to be inserted, noting that there is a small pin to prevent rotation, which engages with the clamp plate. The cylinder specimen is inserted into the line contact specimen carrier and the grub screw lightly tightened. it is important to ensure that the cylinder specimen is mounted centrally in the carrier to ensure that the specimen itself is uniformly loaded against the flat surface. Rotate the moving specimen carrier to bring the cylinder specimen in contact with the plate specimen. Apply a downward force to ensure that the cylinder aligns with the plate, and then tighten the clamp further. A simple way to check that the line contact specimen is properly aligned is to insert a piece of paper between the cylinder specimen and the plate and apply a downward force. Then examine the witness mark. If you have some carbon paper, inserting that between two sheets of paper and pressing down is another way of generating a good witness mark. Area contact specimens are driven by a bullet-shaped driver which is fitted to the reciprocating head. Rotate the reciprocating head to bring the driver into contact with the moving specimen. Make sure that they align. Double-clicking the compend icon on the Windows screen launches the software at page 1, the primary user interface screen. A single screen or page contains up to 40 boxes, and there are a total of 6 pages. Page 2 is for manual control of the high-speed data acquisition channels. Pages 3 and 4 are available for controlling additional peripheral devices if required, and for additional sensors and derived channels. Page 5 is used for calibration. Page 6 duplicates boxes from page 1 and is used to define the order of columns in data files. It may also contain machine status information that can be used for fault finding. The current page number is shown in the top right-hand corner. The page displayed may be changed with a right or left click of the mouse, or by pressing the page up or down key on the keyboard. The software version number and the installed system configuration are shown at the top left of the screen. In this example, the configuration is for a T77 machine. Clicking on the File menu and selecting Show Setup displays the current setup and calibration files. The green boxes on the status bar show the peripheral devices under the supervisory control of the compend software. In the case of the T77, there are 4 such devices. The slim box refers to the Serial Link Interface module, which provides a microcontroller-based distributed control and data acquisition interface between the front-end software and the machine. A green box indicates that two-way communications has been established between the PC and the interface. At startup, or when a different configuration file is loaded, the slim box will temporarily turn blue while the software configuration is downloading from the PC to the microcontroller. It will revert to green once the software has been successfully downloaded. The box marked CT drive indicates communication between the PC and the motor vector drive, which is under direct digital control. The box marked K5018 indicates communication between the PC and the Kistler charge amplifier, which is used in conjunction with a piezo transducer to measure the friction force on this particular machine. The box marked DT-HSD indicates communication between the PC and the high-speed data acquisition card. The digital boxes on the screen are all color-coded to indicate function. Red boxes indicate outputs to the machine, including switches and set points, and with a few exceptions will have up and down toggle switches. Green boxes are inputs from machine sensors. Blue boxes are calculated channels derived from a number of sensor inputs. If a peripheral device box on the status bar turns from green to white, this indicates a loss of two-way software communications between the front end and the device. If the box turns red, this indicates a hardware fault with the comms port or the associated interconnecting cables. All peripheral device boxes must be green for satisfactory operation of the machine. With the software loaded, pressing the blue reset switch on the instrument panel enables the load actuator. The corresponding box on the screen changes from disabled to enabled. The loading system is now live and the load yoke can now be engaged. Do not attempt to start a test without first engaging the load yoke. We can now run the machine under manual control. To apply a load, use the up and down arrows on the side of the red load setpoint box to adjust the load to the required value. Alternatively, you can double click on the setpoint box and insert a value using the keyboard. The resulting load, as measured by the loading system force transducer, will be displayed in the adjacent green load box. To set the charge amplifier for friction force measurement, use the up and down arrows to scroll between short, medium and long time constant. Short and medium are used for dynamic force measurement, and long is used for quasi-static force measurement. Short is used for tests above 2 Hz reciprocating frequency, medium for tests between 0.5 and 2 Hz, and long for low reciprocating velocity tests using the optional reduction gearboxes. The long time constant is also used for calibration. Next, choose an appropriate friction measurement range for your test. Then click the up arrow on the friction measurement box to download the settings to the charge amplifier and enable the measurement. The measure value will now be displayed in the green friction force box. This is the time smooth friction force value generated by passing the instantaneous friction signal through a true RMS to DC converter. The friction noise reading is an analog measurement of the orderliness or smoothness of the instantaneous friction signal. Please refer to the manual for further information about friction force measurement and signal processing. The value in the blue friction coefficient box is that derived from dividing the time smoothed friction force signal by the measured load. The fixed specimen heater can now be enabled by clicking the up arrow on the red heater box. The temperature set point can now be set in just the same way as the load set point, using either the up and down arrows or by double clicking on the box and entering a value with the keyboard. The temperature as sensed by the thermocouple in the side of the specimen bath will be displayed in the green specimen temperature box. Note that large step changes in temperature set point are likely to cause the bath temperature to overshoot the set point. So under manual control, use small set point increments when adjusting the temperature. This issue is avoided with automatically controlled tests, where it is recommended that ramped set point changes are used. Having first confirmed that the test specimens have been fitted and the loading yoke has been engaged, the motor can now be enabled by clicking the up arrow on the red motor box. The frequency set point box can now be used to set the reciprocating frequency in just the same way as the other set points. The measured frequency is displayed in the green frequency box and the number of cycles in the green total cycles box. The count can be reset to 0 by pressing the up arrow on the red cycles box. This is a momentary action switch, and the display will revert to count after a few seconds. The final box to note on this screen is the green contact potential box, which displays a time-smoothed output from a Lum-Fury electrical contact resistance measurement circuit. Further details of this measurement technique and interpretation of the results are given in the manual. To record data while running under manual control, click on Data File on the toolbar and select Open Immediate Data File from the drop-down menu. This will open the Compend Immediate Data File directory. Either choose the name of an existing file to be overwritten or appended, or name a new file, then click Open. A drop-down menu will appear from which to select a data rate. 3 new boxes will appear on the status bar. The first of these will display the number of lines of data recorded. The third box shows the selected data rate. Click on the green Start box to start recording data. The box changes to a red box marked Stop. The data lines box value now increases as each line of data is added. To change the data rate while recording, click on the data rate box and select a new rate from the menu. To pause recording data, press Stop. To restart recording, press Start. To stop recording and close the data file, press Stop, then click on Data File on the toolbar and select Close Immediate Data File from the drop-down menu. To view the data file, from the same menu, select View Data File in Excel. Select the chosen file and click Open. The data file will now be displayed in Excel. The data is time-stamped, and the order of the data columns follows the order of the boxes displayed on the screen page 6, reading top to bottom and from left to right. So in this case, the spreadsheet columns will appear in the order friction force, contact potential, load, friction noise, etc. All boxes marked with a green square in the bottom left-hand corner will appear in the data file. To open an auto-scaling real-time graph, select Graph on the toolbar and create graph from the menu. The channels currently displayed are shown in the panel on the right hand side. To edit the channel selection and change scales, click on Edit followed by Edit Graph Connections. This opens a new panel. To change the scale of a channel, select the channel from the list and edit the minimum and maximum values as required. Click OK to accept the change. In this example, we have changed the friction force range from 0 to 100 to 0 to 10. To remove a channel, return to the graph panel, select the channel to be removed, click Disconnect, followed by OK. To restart the graph, select Graph on the toolbar and Reset Graph from the menu. To add a new channel, return to the graph panel, select an unused graph connection in the left-hand window. The right-hand window lists all available channels. Select the channel you want and click Connect. Next, set a minimum and maximum value and click OK. The new channel is now added to the list of channels displayed and the trace appears on the graph. The graph is auto-scaling, so the trace is progressively compressed, with the 0 on the time axis, the time when the graph was last started. This allows the operator to view the entire test from that time to the current moment. To close the graph, click on File on the graph toolbar and select Close Graph. High-speed data acquisition can either be triggered manually or automatically programmed within a test sequence file. Manual controls are on screen page 2. The sampling rate and sample size can be set in the boxes provided, and the sampling executed by clicking on the up arrow in the HSD trigger box. This will sample all the inputs physically connected to the high-speed data acquisition interface. The sampled data is displayed in a new graph window. Note that this is overwritten every time that high-speed data is triggered. The window can be repositioned on the screen as required. In much the same way as the low-speed data graph, the high-speed graph can be rescaled by clicking on Edit and amending the values in the table presented. The associated data file can be accessed from the C-Compendex data directory and is called DT-HSD. In the case of the T77, 3 inputs are connected to the high-speed data acquisition interface: the friction force voltage, the reciprocating stroke length, and the contact resistance signal. A 4th column is shown in the data file, and this is the friction force. This is a derived channel generated by multiplying the voltage from the charge amplifier by an appropriate factor to convert from volts to newtons. Note that this file will be overwritten the next time manually triggered high-speed data is triggered. So if you want to keep the data, save the file under a new name. Clicking on Test Sequence on the toolbar presents a menu allowing the user either to create a new 10 or 20-step test sequence file, or alternatively to open an existing test sequence file. Selecting an existing file and clicking Open generates two new windows. The upper window is Control, which is used to start and stop the test, and also to create a data file. The lower window is Test Sequence, which is used to view and edit the test sequence file. This window can be maximized either by clicking on the Maximize button or by double-clicking on the title bar. The control panel can now be minimized by using the Minimize button. Selecting File on the toolbar and Save from the drop-down menu will save the file. Selecting Save As will allow the file to be saved under a new name. The file name is shown at the top of the spreadsheet. Selecting View on the toolbar, followed by Reveal Comment column from the menu, will add a column for adding notes about the test. The next column is Step Number, which is the logical order of steps, but not necessarily the sequence in which they are executed. This column is followed by the Next Step, which defines the step-to-step sequence, hence the actual sequence of steps in the test. This column includes the facility to include loops and calls to subroutines. Right-clicking on the Next Step box will open the parameter window for the current step. In this case, if I click on the Next Step box for step number 1, the parameter window shows Go to Step 2, which is the next logical step, and is entered automatically when the Next Step button is clicked. I can, however, manually enter a different go-to step, should I wish, thus creating a jump. The parameter box also includes facilities for program variable conditions, for executing a step, and for setting a loop count, which appears in the next column. We will cover this later in the presentation. The fourth column is step time in seconds. This can also be used to pause the test, for example, so that the operator can perform a manual task as part of the sequence, or to program conditional steps or jumps. Once again, this will be covered in detail later. Clicking on the step time box opens a parameter window. In this case, the selected step time is 2 seconds. The data mode column shows the data rate programmed for a given step. Clicking on the box opens a parameter box. The maximum data rate for low-speed data is once every 0.1 seconds, in other words, 10 Hz sampling rate. There is also the facility to program opening of a new data file during a test. Data files cannot be viewed when they are being written to, so if you are running a very long test and want to view blocks of data while the test is still running, opening a new data file and closing the previous file will allow the latter to be opened and viewed. The next columns all refer to control parameters, corresponding to all the red box items on the main page 1 screen, including switches and set points. There are also columns for programming high-speed data acquisition, in other words, the red box functions on the page 2 screen. In this example, the first step is used to set up some starting parameters before set point controlled devices are enabled. The temperature set point has been set to 20 centigrade, so that when the heaters are enabled, there is not a large difference between the set point and the ambient temperature. It's also sensible to do such things as including a reset of the cycle counter. It is worth at this stage ensuring that the charge amplifier settings for the test have been entered to avoid forgetting to do so later. Finally, it is sensible to set the frequency set point to 0 rather than a positive value, so that the motion does not start instantly as soon as the motor is enabled. Step 2 includes a comment in inverted commas and a pause. This comment, apply low joke and click on resume, will appear on the screen to prompt the operator to perform some function on the machine. In this case, make sure that he has got the machine physically ready to run the test. To enable this feature, click on View and ensure that there is a tick against the Enable comment window. The pause is programmed in the parameter window for that step time box. The test and the clock will be stopped during the pause and only restart once the operator has clicked resume. Moving on to set points, you will see that the value 0R appears in many places. This stands for zero relative. For example, the temperature set point for step 2 is given as 0R. This means that there is no change relative to the set point in the previous step. So in this case, this temperature set point will remain 20 centigrade. The set point parameter box allows the user to switch between a relative value and an absolute value. At step 3, the temperature has been set to an absolute value of 80 centigrade and a ramp time of 600 seconds. This means that the temperature set point will be ramped from the preceding 20 degrees centigrade to 80 degrees centigrade in 600 seconds. In other words, 1 degree every 10 seconds. Using a sensible ramp time will ensure good control and minimize overshoot of the set point. It is, of course, important to enable the heaters for this step. As well as programming a fixed time for a step, the step time can also be programmed as a conditional step using the associated parameter box. There are a number of conditions that can be selected. In this case, I have chosen step when greater than or equal to. Select any one of these options and a browse list of parameters is presented. I am then prompted to select the source of the conditional parameter, with the choice being from a manual or derived channel or a live data channel from the SLIM unit. As our choice in this case is a live input, SLIM is selected, and then specimen temperature from the list of channels. The trigger value is then entered in the yellow box. The step time box now shows an abbreviation for conditional step positive, indicating that a rising value conditional step has been programmed. The test will now move to the next step once the specimen temperature equals or exceeds 80 centigrade. In this example, a load has been applied during step 3 and the motor enabled during step 4 with a frequency set point of 5 Hz. This step lasts for 1800 seconds, followed by step 5, which includes the exit statement as the next step. This defines the end of the program and closes the test. Don't forget to have both the charge amplifier enabled and data mode set if you want to record any data. If you wish to run a test unsupervised, it is sensible to set alarms in the test sequence file. Click on Alarms on the toolbar. This allows the user to program high and low level warning and shutdown alarms on all analog, pulse counting and derived channels on a step-by-step basis. It is important to note that when a new test is created, no alarms are set. When creating a new test, it is important to set alarms suitable for the test parameters, or as an absolute minimum, use the Set All Steps to Default option to ensure that the test parameters do not exceed the machine's capabilities. Alarms may be set for each step in the test and for each required parameter, although it is usually only necessary to set alarms on the most important parameters, for example, load, temperature and friction. Use the up and down arrows next to the step number box to pick each step. Then set the alarm levels for the required channel from the list on the right. The alarm levels may be copied from one step to another using the copy step and paste buttons. When an alarm is triggered, a message will appear above the control panel and the event will be recorded in the data file. A shutdown alarm will terminate the test. If you have modified the test sequence file, save the changes, then click the Minimize button to revert to the comp-end screen. To restore the control panel, click on the comp-end icon on the bottom toolbar and select the item from the menu. If windows have been resized and moved on screen, the default layout can be restored by clicking Arrange on the toolbar. To run a test, start by clicking Data File on the control panel. Then select Open Data File from the menu. The comp-end data file directory will open. Either select an existing file to be overwritten or appended, or create a new data file by entering a new name, then click Open. The data file name appears in the control panel box. Having checked that the load yoke is engaged and the machine is ready to run, press Start. If you have not previously saved your test sequence file, a prompt will appear. Next, a panel will appear to allow the operator to enter details of the test to be performed. This information will appear at the top of the data file. Once this has been completed, the test will start. The test is at the pause we programmed in step 2, and we have the prompt message on the screen. Once we are satisfied that the prompted action is complete, press resume and the test sequence will continue. It's a good time to restart the real-time graph. The live buttons on the control panel allow the operator to override the test sequence and either pause or stop the test. The next button causes the test sequence to jump from the current step to the next step. When the test has ended, as with the manual test, click on Data File on the toolbar and select View Data File in Excel from the menu. The test sequence file allows loops to be programmed. When used in conjunction with a relative set point, loops allow the user to program incremental steps. In this example, I'm programming a loop to increase the load set point from the current 100 newtons in 100 newton increments up to 500 newtons. To do this, I start by inserting a new step in the sequence. Select the step which is to follow the new step, click on Edit on the toolbar and select Insert New Step. The necessary notes can be added in the comment column and all the subsequent control parameters set, including setting the load set point to 100 newtons relative. A value 100R now appears in the load set point box for the next step. We have to make sure that all the other set points are correctly entered for this new step. Finally, we have to set the appropriate next step value and loop count. In this example, our new step is step 5. So to create the loop, we must set step 4 as the next step. If we now enter a loop count of 4, the test sequence will execute step 4 at the 100 newton load set in step 3, then increase the load by 100 newtons relative to the previous value in step 4. Hence the first loop increases the step 4 load to 200 newtons, the second loop to 300 newtons, the third to 400 newtons, and the fourth and final loop to 500 newtons. On completion of the required number of loops, step 5 will move on to the next logical step, which in this case is step 6. With the load increasing each time the loop is executed, it is important to set the alarms for the steps within the loop to values appropriate for the maximum set point value achieved during the loops. If we now run the test, we can observe what happens on the real-time graph. We will of course have to rescale the graph to accommodate the changed test parameters. To program high-speed data acquisition within a test sequence file, click on the HSD sampling rate box and enter a value. In this example, I'm setting the sampling frequency to 5 kHz. Next, click on HSD samples and enter the number of data lines to be collected. In this example, I have set 5,000 data lines, which means that with a sampling rate of 5 kHz, 1 second of high-speed data will be recorded. Note that the ramp time is not a relevant parameter for high-speed data acquisition. The next column sets the data acquisition mode, further details of which can be found in the manual. The most widely used mode is Mode 1, Internally Pace. This uses the internal clock on the high-speed interface as the trigger. Having set the required high-speed data acquisition parameters, entering 0 relative in subsequent steps will keep the parameters unchanged for those steps. To trigger high-speed data acquisition at various points in the test, we can program a loop. We start by adding a step during which high-speed data acquisition is triggered. In this example, I will amend step 4 to run for 170 seconds with the new step, step 5, during which high-speed data acquisition will be triggered, lasting for 10 seconds. Step 5 then goes to step 4 and the loop count will be set to 9. Hence the step 4 and 5 sequence will be executed a total of 10 times, giving a total runtime of 1800 seconds as before. If we now run the test, we can see what happens. If we want to see the high-speed data while the test is running, click on Graph on the toolbar and select High-Speed Data Graph from the menu. The graph window can be repositioned as required. Every time high-speed data is triggered, the graph window will update. We can move between the high and low speed graphs if required by clicking on the graph icons. Every time high-speed data is generated, a new data file is created and an entry made at the relevant point in the low-speed data file. At the end of the test, we can open the low-speed data file and scroll down to each high-speed data file. Automatically generated hyperlinks are provided for accessing the high-speed files directly from the low-speed data. Alternatively, individual high-speed files can be opened in the compendex data directory. You may want to run tests using a common test sequence, but with changes to a given control parameter. You could, of course, simply edit the test sequence file each time you wanted to change the parameter. Alternatively, the software allows the user to program a variable set point as opposed to a fixed value. The user is then prompted to enter the required value at the start of the test. To create variable set points, click on View on the Test Sequence File toolbar and select Variable Table from the menu. This generates a table for defining variable set points. In this example, I have defined test load, temperature, frequency, and duration as variable set points. Now click on the required set point box, for example, load at step 3. Instead of using a set point of 100 newtons, as shown, click on the Use Variable box and select Load from the list of previously defined variables. The value in the box now appears as a set point of V1. We can now use the other variables as required, for example, V2 as the temperature set point for step 3. We can also use a variable for the value in a conditional step. So instead of using 80 degrees centigrade as shown here, we can choose variable V2 by selecting temperature from the list. Once we have defined all the required variables, we can save the test sequence file and run the test in the normal way. When Start is pressed, the previously defined variable table is displayed. The required values for this particular test are entered. When OK is pressed, the test starts as normal and runs with the set point values defined in the variable table. That concludes this instructional presentation. If you would like to access specific sections, please choose the appropriate place from the timeline.